This is one of a series of revision lectures produced by the Further Maths Support Programme. This one in particular is looking at Edexcel FP1, and the topic is complex numbers. The specification in Edexcel requires you to know that a complex number can be expressed in the form a plus ib, so it's Cartesian form, or in the form r cos theta plus I r sine theta, so it's what's termed as its polar form. This is the idea of the modulus r, so the modulus of the complex number is equal to r. We usually refer to complex numbers as z, so mod z is r, and the argument of, or arg z, is equal to theta, and then so this is sometimes referred to as the modulus and argument form of the number. In terms of the diagram, the geometrical representation, then a complex number is represented by the point on the complex plane where we've got the real axis and the imaginary axis. So we can think about it in terms of its rectangular coordinates AB, or indeed the polar coordinates r and theta, so that we then have the possibility of interchanging between those, so that if z is equal to a plus ib, which is also equal to r cos theta plus I r sine theta, then clearly a is r cos theta and b is equal to r sine theta. So the real part is r cos theta and the imaginary part r sine theta. This, of course, we can see in the right angle triangle here, so a little bit of right angle trigonometry as well gives the same result. The other things that you're asked to pay particular attention to are the idea of the meaning of a conjugate. The conjugate, which is normally referred to as z star, is equal to a minus ib. So in the Argand diagram, then the conjugate of z is a reflection in the real axis. So z star is down here because we've then made the imaginary part negative of what it was. So we get that reflection going on. The conjugate is very useful because z multiplied by z star is a real number rather than being a complex number, and z star is equal to a squared plus b squared. In other words, it's r squared because of Pythagoras' theorem. The specification goes on and asks us to be aware of how to sum and obviously subtract the sum and difference of complex numbers, and then the product and quotient. Sum and difference is simply a matter of adding the real parts together and the imaginary parts individually. The product of two numbers is done in a way of using the multiplying out two brackets. So for example, if we had 2 plus 3i multiplied by 4 minus 2i, then the real part would come from multiplying the 2 and the 4, and also from the 3i multiplied by 2i. And I won't complete that one, so I'm sure you're familiar with that, but just to remind you that I squared there is equal to -1. Quotient, on the other hand, 2 plus 3i divided by 4 minus 2i. We do it in a similar way to rationalising the denominator with surds, and we multiply this numerator and denominator, the top and bottom, by the conjugate 4 plus 2i, both the top and the bottom. Now the point here is that when we look at the denominator, this will give you on the denominator 4 squared. The imaginary parts are positive and negative each other, they disappear, but then we've got minus 2i squared, and because I squared is negative 1, that becomes plus 2 squared. So there's that a squared plus b squared that we talked about earlier on. The top line, by multiplying out using the brackets or the indeed FOIL, where, as I say, the real parts come from the first and the last part of the calculation, and the imaginary part coming from the outside pair. Here, this is an imaginary, and the inside pair. So far, 4 parts of that calculation. You're asked to be able to represent these onto an Argand diagram. It's possible that you may look at the sum and difference in terms of vectors in the Argand diagram. So just a brief note about that. If you have two numbers, Z1 and Z2, represented by these vectors, then their sum comes from vector addition, so it's at the diagonal on the parallelogram, so this would be Z1 plus Z2. Finally, in the specification, some awareness that if you multiply two numbers together, then their moduli multiply is required. And although some of you may have been taught this, it's not a requirement, so definitely not a requirement to know that when you multiply two numbers, their arguments add. However, knowledge of that, I suppose, is worth having if you have. It's having dealt with the complex numbers basics of, then we go on and look at using them to solve quadratic equations, and in fact higher order polynomial equations, probably cubic, sometimes up to power 4, by the same sort of methods as you would use in C1 and C2. So you'd be expected, for example, to complete the square or use quadratic formula. Just note then, if you have a quadratic now, for example, z squared plus 3z plus 5 equal to 0, this will have two roots in complex numbers, and you should be aware that the roots of a quadratic in this form are of the form a plus ib, and the other root is z star, so perhaps I should really write that as z2 is equal to z1 star, so it's the conjugate a minus ib. The other thing which is worth being able to do is to think about the roots in terms of building up an equation. So if you know that we have two roots as was shown here, then we can write those in the form z minus z1 and z minus z2 in terms of the factors then of the polynomial. So z minus a plus bi and z minus a minus bi. And when you multiply this out, this would be equal to 0, that's our quadratic. When you multiply this out, you will get z squared. The z part coming from here will be minus az from this one and minus az from the multiplication there. So we get minus 2az. The imaginary part of that multiplication disappears again because we've got minus bi here and plus bi z here. And finally, the outside pair, I beg your pardon, the last pair, a plus bi and a minus bi, well, as before, when you multiply z and z star together, you get a squared plus b squared. So this is a useful technique for building up a polynomial equation from the roots that you're given in a question. Okay, moving on to some exam questions then, looking at this topic. Here's a fairly typical early question, an exam paper, this one particularly early, question 1. So the first part is simply showing that z squared is equal to something, actually given that. Well, this really is just a case of saying that z squared is equal to 2 minus 3i multiplied by 2 minus 3i, and then multiplying that out to give you 4 minus 6i minus 6i and plus 9i squared. Now, in terms of the marking for this, you must say something along the lines that but I squared is equal to negative 1, and therefore we get negative 5 minus 12i. If you simply jump from the line which has plus 9i squared to an answer of negative 5, then you're not going to get the second mark. Either a statement here, I squared equals negative 1, or another line showing how that changes to minus 9 at the end of here. I think preferably I would say but I squared equals negative 1, and therefore perhaps even do both and show that third line in here as being 4 minus 12i minus 9. So the first mark is simply for doing the multiplication here, and the A mark is for showing the fully correct solution. Obviously you're given the answer, so you have to show those sufficient steps in there. Part B of the question asks for mod of z squared. So if I look at part B, just at the bottom of the page now, part B, mod z squared, that is just a case of using Pythagoras' theorem. So putting in the values, negative 5 squared plus negative 12 all squared, and that comes out to be root 169, which is 13. So 2 marks there, 1 method and accuracy. Straightforward. Part C, the argument. Well, using knowledge of what the argument means, we use the angle tan inverse. However, you have to be careful with arguments to make sure that you've got the complex number in the correct position of the argand plane. So in this particular case, because z squared is negative 5 minus 12, z squared is in this third quadrant here. The argument is this angle here, and it's going to be negative, so it's going to be in radians, and we want to work out from the diagram. We can see that this side of the triangle 5 and 12, so theta is going to be we're working in radians here, theta will be pi minus tan to the minus 1 of 12 over 5. That's equal to 1.97 to 2 decimal places. So argz is negative of 1.97. We've already shown z squared as a sketch on the Argand diagram, so the final part is also to put z on there. Not a case of putting in z at 2, negative 3. So I just changed to a different colour, z in about here. On the exam sheet there is often a grid for you to use, but if not, a sketch and marking in the values. So this will be at 2 and negative 3 for z itself. Okay, the marking there is relatively straightforward. The method and accuracy marks in each of these. The method mark for the modulus and accuracy, and again the method mark for getting theta, and then accuracy, making sure that you get the negative in there. Remember that the argument goes between negative pi and pi in radians. You would probably get marks if you went round to a complete in a circle. However, really it should be lying between negative pi and pi, so you have positive and negative values for the argument. The next question that I've got on screen is the last two parts of June 2011 question 2. The first two parts had been again to find the modulus and argument of a given number. However, this part is looking then at solving a quadratic equation. Now you can use, as I said before, the methods from core units, whichever you prefer. This one I think lends itself to finding the roots using completing the square, in that it is a relatively straightforward thing to do. So for part C I would go from here and say that this implies that z minus 5 all squared minus 5 squared plus 28 is equal to 0, and therefore z minus 5 all squared is equal to negative 3, and that gives me solutions z equal to 5 plus or minus root 3i. The marking for that is quite straightforward. The method mark for attempting to complete the square, and then for using the square root of negative 1, or the square root of a negative number including I, and then an accuracy mark for getting the two roots correct. To show these on an Argand diagram, well, the essential part would make sure that your diagram is labelled, so you're labelling real axis, and imaginary axis. The Z1, the two values here that we'd found of Z2 and Z3 would then be shown as a symmetric pair here on the axis, so that they're conjugates of each other, 5 plus root 3i and 5 minus root 3i. The other point referred to in the question, the Z1, was 2 plus I, so that obviously is in the second quadrant of the circle. I beg your pardon, negative 2 plus I in the second part of the circle. So here we have our Z1 and here Z2 and Z3. The important thing is that your diagram is reasonably accurate, so that relatively the numbers are to scale. And also, vitally important, is you show the conjugate pair as being a reflection in the real axis. Well, for the final question then, another solution of equations, looking at roots of equations, slightly more complex. This one is it's looking at a cubic, and I've chosen it because it illustrates the other type of question where you're using given roots to find values in a polynomial rather than having to find the roots themselves. However, the first part does use the idea that you know the roots are the complex roots rather are in conjugate pairs, so that if 5 plus 2i, then to simply write down the other root is 5 minus 2i. We then need to find the values of c and d. This has different methods of doing it, although the usual method is to write the polynomial in its factorized form using the roots that you know. So we can write the polynomial as x minus 2 and then multiplied by x minus, and then the second root 5 plus 2i, and finally the third one, x minus 5 minus 2i. Note the use of the brackets there, the small brackets, to make sure that you get the signs correct here. It's x minus alpha, x minus beta, x minus gamma for your three roots. If we then look at the complex ones first of all, and we need to multiply this out to give us a quadratic, well, that's going to be, as usual, multiplying out here, x times x, x squared. The term of x comes from the two parts here, x multiplied by the one complex root and x multiplied by the other. One of them giving you plus 2i x and the other one giving you minus 2ix. So the imaginary part cancels out, and the other two parts are equal, minus 5, so we get in total minus 10x. Finally, the last part of the multiplication is the two complex roots there multiplied together, and because they're conjugates, you're always going to get there the a squared plus b squared. In this particular case, we've got plus 5 squared plus 2 squared. That then needs to be multiplied out to give you the cubic. You could actually simply go for comparing the coefficients of x and d at this stage. If you wish, it is possible to do it, but I'll fully multiply this out to see what we get. The x cubed term is simply just x cubed minus 12x squared. Well, we could take that as read. We're given that in the question if we look up the top here. However, just to check where it comes from, we've got minus 2x squared here, and then there is a minus 10x squared. So worth doing that just to check that we're on the right track. So minus 12x squared. The x term comes from two places. The x multiplied by minus, beg your pardon, the x multiplied by the number term at the end here, which is 29, and then the minus 2 multiplied by the minus 10x here. So in total, you've got there 20 and 29, so in total we've got plus 49x. And then the number term, negative 2 multiplied by 29 is negative 58. So there we are, multiplying out the factorized form, and of course now we can compare the coefficients, and clearly we have that c is equal to 49 and d is equal to negative 58. The marking for this, it's actually a lot of method marks here. You get method mark for the multiplication of the complex factors, so just writing it down here gives you a method mark. Then managing to achieve a quadratic from that of any form as long as I has disappeared is a second method mark. The third method mark comes from multiplying by the linear factor once you've done that, and then the final two marks are accuracy marks, A marks, for these two answers here. Note that if you make an error in finding the quadratic here, you're not going to lose the method mark, but obviously you won't be able to gain the final two marks. So if you make an error in this calculation here, then you're going to gain a maximum of 3 marks there. The final part of the question, similar to the ones we've looked at before, is looking at the Argand diagram again, and I'll just sketch that very, very briefly at the end, just to point out the salient facts about it. Again, as we've discussed before, you must show the conjugate pair. Here we have 5 plus 2i and 5 minus i, so you must show those as being reflective of each other. So we've got put some scaling on here. So this is 2, 4 and 6, and this is my real axis. Then we have 2 of the roots in that sort of fashion, and the third root is at 2, so there we are, our roots alpha, beta and gamma, and we should label this axis imaginary axis, and of course this value here is at 2 and this one at negative 2 on the imaginary axis. So that's a simple 2 marks for showing those with this, again, important feature that the conjugate pair have got reflective symmetry in the real axis. Right, that brings to close the session on complex numbers. There are other sessions available for the other subjects in FP1 and then for the other modules for Edexcel and other boards.